If you've heard of resistor-capacitor circuits, or RC circuits for short, you've almost certainly seen this equation, tau equals R times C. This Greek letter tau is called the time constant, which sounds strange because resistance R and capacitance C are seemingly unrelated to time in any way. But they are. In fact, in any circuit containing one capacitor and any arrangement of resistors, this single number tau decides how fast the capacitor charges and discharges. It dictates exactly how the charge in the plates, the voltage across them, the energy stored in them, and the current through the circuit evolve with time. In this lecture, we'll figure out exactly how to calculate these four quantities at any moment in time during the charging and discharging processes. We'll figure out where the constant tau equals RC comes from, and see what happens when we vary it. So let's start with the charging process of the most basic RC circuit, consisting of a battery, a resistor, and a capacitor in series. Our goal is to find the charge in the plates Q, the voltage across the plates V, the energy of the plates U, and the current through the circuit I, at any moment in time. So we will start by writing these variables as a function of time t. The first thing we can do is list what we already know about our circuits, regarding the three components in it. The first is the constant battery voltage, which we'll label V0. As always, there is a small internal resistance, but to keep things simple, we'll ignore it. The resistor, meanwhile, has a constant resistance R, while the capacitor has a constant capacitance C. We established all this back in videos 5, 6, and 9 if you need help. So how do we solve this system? Well, of course, as for any DC circuit, we can apply Kirchhoff's laws, which we discussed back in video 8. Let's start by applying Kirchhoff's current law, which in a series circuit is incredibly simple, stating that the current through any point in the circuit is the same, whether it's through the resistor, the capacitor, or the battery. Kirchhoff's voltage law yields something more interesting. In this case, the voltage is provided entirely by the battery, so the fixed battery voltage is equal to the voltage through the resistor, which we'll label VR, plus the capacitor voltage V. Both of these quantities are going to vary with time, while the battery voltage stays fixed. Our goal from here is to find a way to write this equation in terms of the constants we know and one of the variables we don't yet know. How would we do this? Well, we know from our capacitance equation, C equals Q over V, that the ratio of Q and V in a capacitor stays fixed. So, we can write V across our capacitor as Q over C. Why is this useful? Well, the voltage drop across our resistor is the current I times the resistance. What is the current? Well, by definition, it is the change in charge over the change in time, and in differential form, we can write this as dq by dt. And what's beautiful about this is that this Q is the same as the Q in the plates, because according to Kirchhoff's current law, if the current is the same through our entire circuit, then the charge going into the plates at any moment must be the same as the charge going through the resistor. So, we can rewrite Kirchhoff's voltage law like so, where the constant battery voltage equals the resistance times dq by dt, plus Q over C. This is a first order differential equation, and if we can solve it for the variable Q, we can find the function for Q that satisfies this. If you aren't familiar with how to solve first order differential equations, I suggest looking it up, as I won't spend too long explaining why the following method works here. But anyway, to solve this, our goal is to basically write this part of our equation as the derivative with respect to time of one function in brackets. First of all, we divide by r to remove the constant in front of dq by dt. Then, we use a very clever trick where we multiply the entire expression by something called an integrating factor, which is always equal to the exponent of the integral of the coefficient of our variable, in this case q. So, it is e to the integral of 1 over r times c with respect to time t. This is a really easy integral, equal to t over rc plus a constant a, so our integrating factor is e to the power t over rc plus a, which we can rewrite as a constant b e to the t over rc. Multiplying our entire expression by this, we get this, so we can automatically cancel out this unknown constant b. Now our equation is in this form. We can now see that almost by magic, we can factor out the d by dt like so. If you're not convinced that this line equals the previous line, feel free to pause the video and evaluate this derivative yourself. Anyway, this is now an easy equation to solve, and we can do it by simply integrating both sides, which is easy to do. On the right-hand side, this removes the derivative term, and on the left-hand side, we just need to integrate this with respect to time. Integrating exponentials is easy. It's just 1 over RC times e to the t over RC. So our left-hand side expression becomes the constants v0 over r times RC times e to the t over RC plus a constant b in brackets. Expanding this, we'll rewrite b times the constants as another unknown constant d. All in all, we get this expression, and to make it look neater, we'll move our e to the t over RC terms to the same side and factorise, leaving the constant d equals q take v0 c times e to the t over RC. This might look strange, but we now have an equation relating the charge on the plates q to the time t. We can get rid of this unknown constant d very easily by considering the initial conditions of our circuit. At a time t equals 0, we know the charge on the plates must be 0. If we substitute these conditions into our equation, we get d equals 0 take v0 times c times e to the 0. So d equals minus v0 times c. Therefore, we can rewrite our expression for q as follows. We can rearrange this to more conveniently write q in terms of time t. If we divide through by e to the t over rc, we get minus v0 c times e to the minus t over rc is equal to q minus v0 c. Finally, we can write q equals v0 c times 1 take e to the minus t over rc in brackets. This is our final expression for q in terms of time. This answer might seem quite complex and random, but we'll see in a minute that this expression is really quite amazing, and it's beautiful how it appears after all that working. So let's now look closely at it. First of all, we see that we have the battery voltage times the capacitance, which you'll notice is oddly familiar to our capacitance equation. In fact, this product is the charge in our plates when V is equal to the battery voltage, which is when our capacitor is fully charged. We can therefore write this as Q0, which denotes the charge on the plates when the voltage across the plate is equal to the battery voltage, i.e. fully charged. Then we have this 1 minus e to the minus t over RC in brackets. This factor has no units, and it describes the charge at any moment in time. If we plot the graph of Q versus T, you'll see something like this, where initially Q rises very quickly before exponentially tailing off to the maximum value Q0. This exponential decay makes complete sense as charges repel. If there is more charge on the plates, it is harder to push even more charge in. Ignoring the constants for a moment, if we look at the extremes at t equals 0, the exponential is equal to 1, so the brackets are equal to 0. So the charge is 0. If we then charge our plates, as t tends to infinity, the exponential tends to 0, so the brackets tend to 1. Therefore, our charge tends to Q0. But why is the resistance and the capacitance in this exponential? Why would they be linked to the time variable? To answer this, let's first look at the units of resistance and capacitance. Resistance by definition is volts per amp, while capacitance by definition is coulombs per volt. So, R times C means we can cancel the volts to leave coulombs per amp. By definition, amps are coulombs per second. So, we get coulombs per second, but we can cancel the coulombs to leave seconds. So yes, resistance times capacitance means time. This probably seems absolutely insane to you, as how on earth can a property of a resistor times the property of a capacitor be time? But it's true, and quite beautiful, as these units obviously match the units of our time variable. So, our exponent is unitless, as it should be. It's very neat how going through that entire differential equation yields this result naturally. A nice way of thinking about it is by saying the capacitance C determines how much charge we want in our plates for a given battery voltage, while R determines how fast we can move the charge into the plates. This equation really works like clockwork. For neatness, we like to write this constant RC as another constant tau, which we call the time constant. Let's visualize this constant on a graph. When t is equal to tau, our exponent is equal to e to the minus 1, which is obviously a fixed number, no matter what else happens in our system. Our brackets therefore become 1 take e to the minus 1, which always has the value 0.63. So when the time is tau, the charge in our plates must be 0.63 of q0, no matter what. At t is equal to 2 tau, we get 1 take e to the minus 2, equal to 0.87. So for every chunk of time tau, an increasingly small chunk of charge has been moved into the plates. All in all, as long as we know the battery voltage, capacitance, and resistance, using this equation, we can find the charge in the plates at any time t. Let's now figure out the voltage, current, and energy, which will be much easier to do. The voltage, as we know, is just the charge in the plates over the capacitance. So if we divide our charge expression by C, we automatically get the voltage, which is really neat, equal to the battery voltage V0 times 1 take e to the minus t over RC. This makes complete sense, as it shows that our plate voltage is approaching the battery voltage at the same rate that our charge is approaching Q0. As for the current, we know it's just the derivative of the charge with respect to time. If we apply this to our charge expression and expand the brackets, we find the constant term just disappears, leaving us with the derivative of e to the minus t over RC, which is really easy, where we just take the constants out front like so. If we cancel these constants, we find the current to be V0 over R times e to the minus t over RC. V0 over R is the initial current in our circuit, which we'll rewrite as I0. So this expression is a little different to the others, but it makes complete sense as the current starts at a very high value, then exponentially decreases as more charge is in the plate. But what's interesting is that we have the same exponential here, which means that the current changes at the same rate as the charge and voltage. This is because they're all controlled by the same physical process, charge flowing through a resistor into a capacitor. Now there's one more quantity which is useful to us here, which is the plate energy. From the previous lecture, we found that this is just a half times Q times V. So if we substitute our values in, we get a half Q0 V0 times 1 take e to the minus t over RC all squared. We can say that a half Q0 V0 is the maximum energy U0, while the brackets determine how the energy varies with time. So the energy actually varies in a different way with time. Plotting this, we get the following trend for the energy as a function of time. So let's summarize our results for the charging process. We can see that all these graphs are governed by the same time constant tau, equal to the resistance times the capacitance. We can easily find the values for t equals tau and so on. But what happens when we vary r and c? Well, if we vary r, the graphs vary like so. And if we vary c, this happens. Let's break down each graph individually, as there is quite a bit going on here. First of all, when increasing r, no matter what, tau increases. And as we know, this is the deciding factor for how long the process takes. So the process takes longer now. But there are also the constants Q0, V0, I0, and U0. When varying r, Q0, V0, and U0 stay unchanged, but I0 does in fact vary, as this is equal to V0 over R. If we increase the capacitance, once again tau increases. This time, however, Q0 and U0 also increase, as Q0 equals C times V0, and U0 is a half C times V0 squared. Meanwhile, V0 and I0 remain unchanged. Now to be clear, the main thing we care about here is the time it takes for us to charge our capacitor, which entirely depends on tau. So increasing R or C increases the charging time, and vice versa. So what about discharging? Here the setup is almost identical, but now we start with a fully charged capacitor and no battery. In this scenario, the capacitor acts as the voltage source, driving current through the resistor. Using the same loop as before, Kirchhoff's voltage law now says that the capacitor voltage V plus the resistor voltage VR equals 0. So rearranged, V equals minus VR. Like we did before, we can write this as Q over C equals minus I times R. And since I is dQ by dt, we get Q over C equals minus R times dQ by dt. This rearranges to dq by dt equals minus q over rc. This equation is miles easier to solve than the one we had for the charging process, and we can do so by separating the variables such that 1 over q dq equals minus 1 over rc dt. You can probably already see where this is going. Integrating both sides gives us the natural log of q equals minus t over rc plus a constant a. Taking the exponent of both sides, we get q equals e to the minus t over rc plus a constant a, which we'll rewrite as a constant b times the exponential. In this discharging scenario, we'll say that at t equals 0, q equals q naught, and if we plug these into our equation, we see that q naught equals b. So our final expression is q equals q naught e to the minus t over rc. And that's literally all there is to it. The charge decays exponentially from q naught to 0, with the exact same time constant rc controlling the rate. We can find the voltage just as we did before, as v equals q over c. Dividing through by c immediately gets us the expression v equals v naught times e to the minus t over rc. For the current, I equals dq by dt, which gives us I equals minus q naught over rc times e to the minus t over rc. The minus sign shows that the current flows in the opposite direction during discharge. These constants, as you might have guessed, can be simplified to minus I naught, which is the same initial current from the charging process. So in fact, our discharging current expression is identical to the charging expression, except the direction is reversed. This makes complete sense, as in both cases the current will be largest initially, then it will tail off. In my plot, we've ignored the sign and plotted the magnitude to keep things simple. Lastly, the energy is just a half q times v again, which now yields u naught times e to the minus t over rc squared. It can be plotted like so. If we line up these graphs side by side again, we can see that they are all governed by the same tau as in the charging process. As we vary the resistance, we find the graphs vary in the exact same way as in the charging process, following the exact same rules as before. This goes for varying the capacitance also. So all in all, we get these 8 expressions for the charge, voltage, current, and energy as a function of time for the charging and discharging processes. As you can see, the length of the processes entirely depends on the same time constant tau equals Rc. Therefore, as long as you know the resistance and capacitance, you can figure out exactly how long the charging process will take. Every expression here depends on this exponential decay term. So overall, considering the previous 2 lectures, where we discussed the capacitance and the energy stored in a capacitor, we now have a solid understanding of how capacitors work, at least in DC circuits, which have been the focus of the series up to this point. Everything we've done so far in this series assumes the voltage source is fixed, using a battery of some sort. But in the real world, many electrical systems don't actually work like this. Instead, they use an alternating current, or AC, where the current direction continuously flips. In the next few parts of this series, I want to discuss with you what AC electricity is, how it works, and why we use it. By the way, if you enjoyed this video and like testing your physics knowledge, you're welcome to check out the Decipher Physics app, which is completely free and has over 100 questions for you to work through. Thanks for watching.